Hey, and welcome to the simpler, shorter version of our Capnometry video where we give you just the highlights. As always, this is Russ with Rockwall County EMS, where we've known whether or not Schrodinger's cat has been alive or dead since '96. And you know what? We're not telling. Capnometry and capnography, different, and I'm going to tell you how. Capnometry is the numerical representation of end-tidal sampling and generally displayed right next to a respiratory rate. So here, 36 is our end-tidal capno reading, and 18 would be our respiratory rate. Capnography is the graphical waveform generally below those numbers, a graphical waveform of the same thing, CO2 sampling. Speaking of CO2 sampling, this device here provides for both CO2 sampling as well as the delivery of oxygen to your patient. However, it's important to note the limitations of this device and how it works. So, CO2 sampling happens everywhere you see in blue. Through both sides of that device, air is sampled and sent back to the cardiac monitor where then it's detected for CO2 content. Uh, and then at the front of the device is where oxygen is delivered. So again, you'll note at the front of the device are the holes through which oxygen is delivered. And if you deliver oxygen through this device, really all you're doing is hyperoxygenating the airspace in front of the patient's nose and mouth. And this would require some means of ventilation to get that air from the outside in. So either the patient's own spontaneous ventilatory drive, intact ventilatory drive, or the clinician administering some means of mechanical ventilation. Moving on, we're going to be talking about the lungs, the cells, and the shipping method, i.e. the cardiovascular system to move things to and fro. Overview, simplified, is oxygen comes into the lungs, is dumped off into the bloodstream takes it down to the cells, where it's then utilized for some cellular metabolic process, and then a byproduct is created called CO2. CO2 goes back into the bloodstream, is shipped up to the lungs where it's excreted and exhaled, and more oxygen is taken in, and the whole process starts all over again. Now, it's important to note that this is a super simplified representation of a complex physiologic process. There's lots of things missing here. Also important is the idea that this is one big orchestral performance with lots of moving parts. The lungs are moving air in and out, the shipping system, the cardiovascular system, is moving stuff to and fro, and the cells are continuing on in different parts of the body, different types of cells with their different types of activities. All of this happening in concert. So for our purposes, we're going to remove the oxygen and just concentrate on the shipping system, the bloodstream bringing CO2 to the lungs, and that CO2 being then exhaled into the outside environment. So to get a better understanding, we'll start with a simplified baseline. So normal ventilatory rate, whatever it is, the shipping system is going to bring in that CO2, drop it off in the lungs, and it'll be exhaled, and we're going to count how many go out with one ventilation. So one inhale and exhale produces 16 CO2 molecules here for our baseline. This is just an arbitrary number I chose to establish a baseline, and then we're going to move to tachycardia, or tachypnea rather. So fast breathing. The shipping system works just as it did before. However, because the breathing is happening so quickly, we have little time to collect these CO2 molecules and thus exhale them out into the outside environment. So you'll notice with each single ventilatory cycle, we're only getting a total of 8 CO2 molecules out before the ventilatory cycle starts again. Alternatively, bradypnea, slow breathing, each shipping system, each shipping truck brings in 4 CO2 molecules, but because breathing is happening so slowly, we're collecting an overabundance of CO2 molecules before here even exhalation starts, and by the time it does and ends, we get a total of 32 CO molecules this time for one ventilatory cycle. So real world translation, we use a cardiac monitor, use some sort of inline CO2 monitoring device to detect exhaled CO2, and this would be, again, more akin to our normal baseline readings. So a normal cardiac rate of about 76, well within the normal ranges of ventilatory rate of 14, and then our normal end-tidal should be around 35 to 45. Anywhere in there is acceptable. Now, if we have a tachypnic patient, we have less time to collect that CO2 before it's then exhaled and it's detected for its CO2 content. And so a tachypnic rate would result in a hypocarbic or hypocapnic number, So increased breathing results in decreased end-tidal numbers. Alternatively, bradypnea, slow breathing, would result in more time to collect an overabundance of CO2. And then by the time it's all exhaled, because breathing is happening so slowly, here at a rate of 6, we should get a higher than normal reading on our capno. And of course we do. So a bradypneic rate of 6 results in a hypercapnic or hypercarbic rate or reading of 55. So all this oversimplified, there's lots of things that could complicate this, but that's it in a nutshell. Once again, this has been Russ with Rockwall County EMS, and we'd like to thank our sponsors that made this video possible. Blood and Stuff Transit Company, where CO2 transport is a breath of fresh air.